How's it going, ladies and gentlemen? Mr. Johnny here again, taking a look at some Chapter 15 problems where we're going to talk about equilibrium and the equilibrium constant. So we start off kind of with some easy ones, and then we're going to get into some more complicated stuff. So 1, at equilibrium, at equilibrium, blank. All right, chemical reactions have stopped. That is inherently false. That is not true. So at equilibrium, if we have a reaction, let's say X becoming Y, at equilibrium, there's also a reverse reaction. All right. Equilibrium constant is 0. That is false. Limiting reagent has been used up. That is also false. The rate constant of the forward and reverse reactions, dinner. The rate constant of the forward and reverse reactions are equal. That is also false. It's not the constants that are equal. It is the reaction rates. So the rates of the forward and reverse are equal. Right. All right. So I might have made a mistake on the key. I got the wrong one circled here. Oops. But it's definitely E, right? So equilibrium, it's like running on a treadmill, right? You're going forward, but the treadmill's going back at the same speed, hopefully at the same speed. If you're not going as fast as the treadmill, you're getting thrown off. All right, so what does the Haber process produce? So the Haber process is just, it's pretty important because we use it to make fertilizers and stuff for agriculture. And the process is as such. We make NH3, which is ammonia. So short answer, ammonia. Long answer, this is the equation, and it gives you ammonia. 3. What did I just do? All right, there we go. 3. Which one of the following will change the value of an equilibrium constant? So these things are considered constant, so we know not a lot of things change them. Adding inert substances that are not involved, that's not going to change anything at all. Changing the temperature, yes. Temperature will have an effect on the equilibrium constant. Changing the initial concentrations, not going to affect it. Same with the concentrations of the reactants or products. Changing the volume of the reactant container, not going to affect the constant. Because basically what's happening is, let's say we got this simple equilibrium going on. So it's saying if you start with X, well, it's going to reach equilibrium with Y. And it's in some fixed ratio always. Doesn't matter how much X you start with, you'll end up with a proportional amount of Y. Or vice versa. If you start with Y, you'll end up with a proportional amount of X. All right, well, what's the proportion? Well, that's our KEQ. All right, so it doesn't matter how much of each you start with, it's going to come to this balance, this constant. Only changes with temperature. 4. What is the equilibrium constant expression for the equilibrium between dinitrogen tetroxide and nitrogen dioxide, represented by this equation here? So the KEQ, in general, is always going to be the products over the reactants. And we're talking about concentrations, or we're talking about pressures. Depends on if you want KEQ or like KP. And those are always going to be to the coefficient, which I'm going to just put A and then B. So if we take a look here, N2O4, since it's blank, we know it's a 1, and NO2 has a 2 there. So products would be, all right, concentration of NO2 squared, because of that coefficient here of 2, all over the reactants. N2O4 to the first power, so I don't really got to write it. I'm going to, just so you know, that's a 1 because of the 1 that's been omitted there. 5. What is the equilibrium constant expression for the equilibrium below? So it's just like the last one, except different equilibrium. So you got to remember, KEQ is concentration of the products over the concentration of the reactants. So let's take a look. The products, well, again, we only have 1, so it's CH3OH. Concentration of that, coefficient is 1, so I can leave it blank, all over concentration of each product. So the concentration of CO2, its coefficient is 1, so I can leave that blank, and then the concentration of H2, and it has a coefficient of 2 in front of it, so I gotta square it. That's all that is. 6. What is the Kp? So now here, the P is saying, hey, equilibrium constant, but in terms of pressure. So we're dealing with gases, so we go, all right, well, again, Kp is products over reactants, so I put pressure of my O2 instead of concentration to the third power all over the pressure of my O3 to the second power because of the coefficient. So that's all it is. Right, let me get caught up. 7. Given the equilibrium below, equilibrium cannot be achieved when blank is placed in a closed container. All right, so let's think about this. If we added NO2 and O2, all right, well, we have all of the reactants we need to make the product. We would be able to get an equilibrium there. If we added NO2 and NO3, well, let's think. We added one reactant and we added all of the product. Right? There's only one product, so if we got it there, we know we can get that reverse reaction going. So this would form an equilibrium. If we added some O2 and some NO3, so again, O2, we added some reactant, but we added all the products we needed for that reverse reaction. Let's see if this eraser works for me. Sweet. So this C would also form an equilibrium. If we added 0.75 moles of NO2, well, let's think about this. If I just had NO2, how am I going to make NO3 if I don't have O2? Short answer, you can't. So this one is not going to reach an equilibrium. But then, Mr. Johnny, what about this? We only added just NO3. There's two other things. Right. But we added everything that was a product. We only have one product. If we start with just that, that's all we need to establish an equilibrium. That's all we need to make the NO2 and the O2. 8. The equilibrium constant expression depends on blank of the reaction. So again, you remember KEQ equals the concentration of the products over the concentration of the reactants and the coefficients, which I'm going to use A and B as variables. So this depends on temperature. Actually, no, the value will depend on temperature, but the expression itself is going to depend on the coefficients, other reactants and products. These things, nope. Expression, without numbers plugged in or anything, that's the only thing that changes it. So 9, equilibrium constant for the reaction below is blank. So, actually, they give us that. They give us a value. And it says at equilibrium, all right, they're looking at products, reactants, and how they're compared to each other. Well, let's take a look at the number. KEQ is 10 to the minus 3, which means it's small. It's a small number. It's a decimal. So we got to remember what our KEQ expression is telling us. It's concentration of the products over the concentration of the reactants. Well, let's think about this. If it's small, then we must have a lot of whatever's on the bottom and only a little of whatever's on top. So we got more reactants than we do products. So which option is consistent with that? E. There are more reactants than products. 10. Equilibrium constant for the reaction blank is a number at a given temperature at equilibrium. So it's just like the last one, except we got a different KEQ. So here we got a KEQ that's large. We're timesing it by 100. So we know we got a big number. So again, KEQ is going to essentially be the products over the reactants. And if it's a big number, that means we got a lot of the stuff on top and only a little of the reactants. Which one is that? It is D. There are more products than reactants. 11. The equilibrium constant for reaction A is K, and it wants to know, well, what is it for reaction B? Well, let's compare them. Let's see what's different. We got NO2, 1/2 O2 giving me NO3. Here I got 2 NO3 giving me 2 NO2 and 1 O2. So we flipped it, and we doubled it. All right, well, let's think about this. If I had KEQ, and it's supposed to be products over reactants. All right, well, if I did the reverse reaction, it would be reactants over the products, which, what does that do for our KEQ? Well, that would equal 1 over that K. All right, and if I doubled it, if I change my coefficients, that's going to change the powers as well. So I'm basically squaring this whole thing. So 1 squared is 1. K squared is going to be K squared. So our final answer is going to be 1 over K squared. We flipped it, which is why we got the inverse, and we doubled it, which is why we got that 2 as the coefficient. 12. The value of KEQ for the following equilibrium is 598 at a given temperature. What is the KEQ for the following equilibrium below? So let's think about this. We got H2, I2 giving me 2HI, and then I got half of that reaction. All right, well, I know KEQ, again, is the products and stuff over the reactants. And if I were to cut it in half, what I'm doing to the coefficient is I'm also putting it in half. So the KEQ is going to be to the 1/2 power, which is the same thing as saying the square root of that K. So we got the square root of 598 because it's given to us right there. And we get 24.5. So 11 and 12 could definitely be in the next section. But, you know, why not challenge ourselves with some good old chemistry? So 13, given the following reaction at equilibrium at 300 K, if PCO2 equals this, what does the Kc equal? All right, so this one probably could have been saved for a later section, but let's talk about it right now. So the KEQ, again, is going to be the products, concentration of the products over the reactants. Now, so far, everything we've done has been a homogeneous equilibrium, meaning everything's in the same phase. But if we take a look at this one, we got 2 solid things and 1 gas. Now, an interesting thing happens when we're talking about the KEQ expression. Right, we're only interested in things that could vary. If we got a solid, well, the concentration of a solid is constant. It doesn't matter what it is, it's not going to change. It's constant. So we can omit it from our constant expression because our expression is for the things that change. Concentrations can be different. So any solids will drop out of our expression. So if I were to initially write it, it would probably be looking like this. CaO, CO2 all over CaCO3, and I'm going to write in the phases now. Solid, CaO was solid, and CO2 was a gas. Solids, being constant concentrations, are going to drop out of our expression. Same thing is for if it was a liquid. If they were both liquids, well, again, liquids are pure substances, and at the temperature, they're the same, you know, they have a constant concentration, so they're going to drop out. So what they really just told us was, well, Kp is 0.0225 atmospheres. All right, well, the Kp expression is really just the pressure of CO2. Coefficient of 1, so I don't got to do anything to it. So they're really telling me that the pressure of CO2 is 0.0225 atmospheres. And what they want is the Kc. So we got to convert this pressure into a concentration, right? We got to get it into molar. All right, well, let me erase and make some room for my future work. So if we know the pressure, now we got to figure out concentration. We're going to have to call upon some equations from units prior, you know? So we got here Pivnert, right? If we know pressure, we know temperature, and they want concentration, well, concentration's amount over volume. So we know that we want our Pivnert equation. All right, well, if they want concentration, they really want moles per liter. So we got moles over here. Well, let's divide each side by the volume. So I got moles per liter right here. And then, all right, well, I want just moles per liter, so I got to get rid of this RT stuff. So I divide RT to the other side, and I'm left with moles over the volume, which we'll put in liters, has to equal the pressure over R times T. So now it's just a plug and chug. We know the pressure, it's 0.0225 atmospheres. The R is a constant. You know, you got to make sure you use the right one, depending on the units, atmospheres. So I use 0.08206, and then I times it by 300K. Now I just use my handy dandy calculator, beep, bop, boop, and I get 0.000914 molar. Because of the units on this, is going to end up in moles and liters. So good to go. So this is my final answer. Again, this problem could have been saved for later in the chapter, but hey, I didn't save it. Same thing with 14. All right. The following reaction is at equilibrium if PNH3 equals the pH2S. So they're saying these two things have equal pressures. What is the Kp? So like I said before, hey, look, it's a solid. So I know that's going to drop out of my expression. So my Kp is really just going to be the pressure of NH3 to the first power times the pressure of H2S to the first power. So now I just plug and chug. It's going to be 0.605 times 0.605, and I get 0.366. And that is my final answer. All right, well, I hope you guys found that helpful. I'll see you in class.